Welcome to Tech Girl Kannada YouTube channel.
Superconductivity. For a material of uniform cross-section, the resistant R is directly proportional to its length and inversely proportional to area of cross-section. R is proportional to L by A. Therefore, R is equal to rho L by A or rho R A by L, whereas rho is a constant of proportionality called resistivity and is defined as the property of a material that gives the measure of opposition offered during the flow of current. Mobility, mu. The mobility of electron is defined as the magnitude of drift velocity acquired by electrons in a unit electric field. Mu equals to Vd by E. Concept of phonon. When a metal is at a temperature well above 10 Kelvin, the positive ions, which are arranged in a periodic array, start vibrating like harmonic oscillators. Since the ions are bound to each other through elastic and electric forces, they vibrate similar to standing waves with fixed energies. The ions may vibrate either due to their own thermal energy or outside forces may make them vibrate. This kind of vibration generates mechanical waves that carry heat and sound through materials. A packet of these waves can travel throughout the material with a definite energy. So, in quantum mechanical terms, the waves can be treated as a particle called phonon. A phonon is a definite discrete unit or quantum of vibrational mechanical energy, just as a photon is a quantum of electromagnetic or light energy. The phonon concentration is strongly dependent on temperature. At low temperature, phonon number is considerably low and is proportional to TQ, whereas at higher temperature, the phonon number is proportional to T power 5, where T is absolute temperature. Matheson's rule. Effect of temperature and impurity on resistivity. According to Matheson's rule, the total resistivity rho of a metal at any given temperature is sum of the resistivity due to impurity scattering and phonon scattering is given by rho is equal to rho I plus rho FPH. The resistivity due to impurity scattering is also called residual resistivity and arises due to scattering of electrons by lattice imperfections and impurities present in a metal. The phonon scattering is due to lattice vibration at a temperature well above 10 Kelvin. Here you can see the graph of temperature versus resistivity where it increases at certain point very high. Initially at 0 Kelvin there will be some resistivity which is called initial resistivity. Introduction to superconductors. As the temperature of certain materials is reduced, the resistance offered by them to flow of electric current decreases. The resistance abruptly drops to zero below a threshold temperature. The phenomenon is called superconductivity and the threshold temperature is called critical temperature or transition temperature. The materials exhibiting superconductivity are called superconducting materials. H.K. Once was the first to observe superconductivity in mercury in the year 1911. He also found that materials regain resistivity when heated above transition temperature. That is, the transition is reversible. Subsequently, superconductivity was discovered in lead, zinc, aluminium, and other metals, as well as in number of alloys. Superconductivity was strictly a low temperature phenomenon till 1980s. In 1986, high temperature superconductivity was discovered in a particular type of ceramic, which remained a superconductor at a temperature as high as 30 Kelvin. Temperature dependence of resistivity. The dependence of temperature resistance of a superconductor on temperature is shown in the figure. The resistance of a materials in non-superconducting state decreases as with the decrease in the temperature. As in the case of normal metal, up to critical temperature Tc, at Tc, the resistance abruptly drops to zero, indicating the transition of material from normal state to superconducting state. The critical temperature is different for different superconductors. For example, mercury loses its resistance completely and turns into a superconductor at 4.2 Kelvin. This is the figure, which is rho versus T again, showing the superconducting phase of a material and non-superconducting phase. Tc is the temperature where the resistance abruptly drops to zero and it becomes superconducting phase. Then again, as the temperature increases, non-superconducting phase also increases. Properties of superconductors. The critical or transition temperature. Superconductors have a certain temperature threshold known as the critical or transition temperature. When the temperature of the material falls below this threshold, it changes from ordinary conductor to superconductor. Zero electrical resistance. The superconductor exhibits zero resistance in its superconducting state. This means that when the material's temperature drops below the critical temperature, its electrical resistance abruptly falls to zero. For instance, lead, a common superconductor, shows zero resistance below 7.2 Kelvin. Exclusion of magnetic field. Superconductors do not allow magnetic fields to penetrate them when their temperature is below the critical temperature. This property is known as the Meissner effect. The critical magnetic field. Superconductors have a certain magnetic field limit known as a critical magnetic field. If the magnetic field exceeds the limit, the superconductor becomes normal conductor. Interestingly, the value of the critical magnetic field is inversely proportional to the temperature. This means as the temperature rises, the value of the critical magnetic field will decrease. Meissner effect. When superconductors are cooled below their critical temperature in the presence of some magnetic field, the magnetic flux is expelled from the interior of the specimen and superconductor becomes a definite perfect diamagnetic. This phenomenon is known as Meissner's effect. This can be further explained as the temperature of the specimen is lowered to Tc, the magnetic flux is suddenly and completely expelled from it. The flux expulsion continues for T is less than Tc. Temperature is less than critical temperature. The effect is reversible when the temperature is risen from below critical temperature. The flux suddenly penetrates the specimen at when the temperature is equal to critical temperature and the material returns to its normal state. Meissner effect is the basic principle behind the operation of Maglev trains. HH, magnetic line of force. Superconductor, when temperature is more than critical temperature, it goes. It expels when the temperature is less than the critical temperature. What is critical field? When a material is cooled below critical temperature, in the absence of magnetic field, the material becomes superconducting. When the magnetic field is applied and as its strength reaches a critical value Hc, the superconductivity in the material vanishes and the material becomes normal. The strength of magnetic field required to just switch a material from superconducting state to normal state is called critical field Hc. At any temperature, the material remains superconducting until a corresponding critical field is applied. When the magnetic field exceeds the critical value, the material goes into normal state. Temperature dependence of critical field. If T is the temperature of a superconducting material, Tc the critical temperature, Hc the critical field, and H0 the field required to turn the superconductor to a normal conductor at 0 Kelvin, then the dependence of critical field on temperature is governed by the following relation. Hc equals to H0 into 1 minus T square by Tc square. Hc equals h naught into 1 minus t square by tc square. The value of Hc varies with temperature as shown in the figure. For a typical superconductor, under the influence of a magnetic field whose strength is greater than h naught, the material can never become superconducting, even if the temperature is very low. Here is the graph which represents the magnetic field and the temperature. Critical magnetic field to H naught, superconducting phase, which the temperature should be less than the critical temperature and field also should be less than the critical field. Types of superconductors. Superconductors are classified into type 1 and type 2 superconductors based on the way in which the transition from superconducting to normal state proceeds when the externally applied magnetic field exceeds critical field. Type 1 superconductors, soft superconductors. Type 1 superconductors exhibit complete Meissner effect in the presence of an external magnetic field which is less than the critical magnetic field. The material is superconducting state is a perfect diamagnet possessing negative magnetic moment. As the applied field H exceeds critical field, the magnetism suddenly drops to zero and the entire material becomes normal as shown in the figure. At this stage, the magnetic flux penetrates throughout the material and resistance raises from 0 to some value applicable to a normal conductor. The value of Hc is too low for critical field is too low for type 1 superconductors. Here is a graph representing the negative magnetic momentum and the magnetic field. Normal state, superconducting phase, and the normal state. It only be in the superconducting phase when the field is less than critical field. Type 2 superconductors, hard superconductors. Type 2 superconductors are characterized by two critical fields, that is Hc1 lower critical field and Hc2 upper critical field as shown in the figure. As the applied field H is increased from 0 to Hc1, the material expels magnetic field from its body completely and behaves as a perfect diamagnet. When H exceeds C1, the flux penetrates and fills the body of the material partially. With a further increase in H, the flux filling also increases, thereby decreasing the diamagnetic property. The flux fills the body completely when H becomes equal to or greater than Hc2. That is when the material becomes normal conductor. Between Hc1 and Hc2, the material is in mixed state, vortex state, in which the material is still a superconductor, though there is flux penetration. Yes. Here is a negative magnetic moment and the magnetic field. Hc1 and Hc2. Hc1 is a perfect diamagnetic phase where no flux penetration occurs until the Hc1, below Hc1. Then after Hc1 to Hc2, there will be flux fills the body completely while partial flux penetration occurs, then it slowly becomes to normal state. BCS theory. In 1957, Bardeen, Cooper, Schrieffer developed a quantum theory of explain superconductivity, which is known as BCS theory. The BCS theory assumed the interaction of two electrons through quanta of lattice vibrations, phonons. The BCS theory assumed the interaction of two electrons through quanta of lattice vibrations. The major features of BCS theory are formation of Cooper pairs and their propagation throughout the lattice without resistance. To understand the formation of Cooper pair, let us consider a situation in which an electron moves through a lattice causing a slight deformation in it. The deformation occurs due to displacement of positive ions in the electron's path towards the electron. The deformation produces a region of increased positive charge. Another electron moving through the polarized region will be attracted by the greater concentration of positive charge. There, if the polarized region will be attracted by the greater concentration of positive charge, there, if the attraction is stronger than the repulsion between the electrons are effectively coupled together to form the Cooper pair. The electrons in a Cooper pair have equal and opposite spins. The binding energy of Cooper pair, called energy gap, is of the order of 10 to the power of minus 3 electron volt. That is why superconductivity is a low temperature phenomenon. Also, according to BCS theory, the energy gap of superconductor at 0 Kelvin is given by the formula Eg of 0 is equal to 3.53 kTc, where K is the Boltzmann constant and Tc is critical temperature. In a typical superconductor, a dense cloud of Cooper pairs forms a collective state, and the motion of all the Cooper pairs is strongly correlated, one aiding the motion of the other. As a result, Cooper pairs drift cooperatively through the material without experiencing any resistance due to absence of scattering. Josephson junctions. Josephson junction is a system of two superconducting metal films separated by a thin insulating layer of thickness 1 nanometer. The superconductor layer constitute Josephson junction. In 1962, Brion-Josephson predicted that Cooper pairs could tunnel through the insulating layer. Superconductor 1, insulator, superconductor 2. The Cooper pairs is in a superconductor can be represented by a wave function, which is same for all Cooper pairs. As the Cooper pairs tunnel from one side of the junction to another, the insulating material introduces a phase difference between the wave functions of Cooper pairs on both sides. Because of this phase difference, a supercurrent appears across the junction even if the applied voltage is 0. This is known as DC Josephson effect. If we apply a DC voltage across the junction, it introduces an additional phase in Cooper pairs during tunneling and generates an alternating current. This is called as AC Josephson effect. Quantum tunneling. A Cooper pair can traverse anywhere in the body of the superconductor, but cannot come out of it, and hence it can be considered as a particle in a potential of wall height more than its own energy. However, a Cooper pair can tunnel through the wall of the potential well if the wall thickness is narrow enough. So tunneling is a quantum mechanical phenomena and is a consequence of the wave nature of the matter, where wave functions describe the state of particle or other physical systems. The particle on one side of the barrier has finite probability of tunneling through it. If there is an allowed state of equal energy available on the other side of the barrier, tunneling is frequent on nanoscale but negligible at the macroscopic level. Particles with a small mass can effectively tunnel through barriers more easily than those with larger mass. Quantum tunneling finds applications in scanning, tunneling, microscope, nuclear fusion, very large-scale integration of electronics, and quantum biology. SQUID. SQUID means superconducting quantum interference device. Superconducting quantum interference device. Magnetic field, Josephson junction, L total, L2, L1, Josephson junction. SQUID is an acronym for superconducting quantum interface device. It is used to measure extremely small magnetic fields of the order of 10 power minus 14 Tesla. A squid is formed by incorporating two Josephson junctions and in the loop of superconducting material as shown in the figure. These are the two types of squids. There are DC squid, RF, AC squid. DC squid. A DC direct current squid consists of two Josephson junctions employed in parallel in the superconducting loop. It is based on DC Josephson effects. It is 1 and 2 Josephson junctions, J, I1, I2 with an voltage. When a constant biasing current I is passed through the DC squid in the absence of external magnetic field, it divides into two parts, I1 and I2. When a small external magnetic field B is applied perpendicular to the superconducting loop, an induced current J starts flowing through the loop. This induced current J generates a magnetic field that opposes the external flux according to Lenz's law. The induced current J supports biasing current I in one branch and opposes the biasing current I in the other branch. As a result of this, the total current increases in one branch and decreases in other branch. When the current in any branch exceeds the critical current IC of the Josephson junction, a voltage develops across the junction. The voltage thus developed across the junction also oscillates with the applied magnetic field. The oscillating voltage can be detected and used to measure the magnetic field. RF squid or AC squid. An RF radio frequency squid is made up of only one Josephson junction, which is mounted on a superconducting ring. It is based on AC Josephson effect and is less sensitive compared to DC squid. RF squid. RF current source, VRF to RF amplifier. An RF squid loop is placed near an LC circuit, which is connected to an RF AC source as shown in the figure. The magnetic field whose flux is to be measured is applied to RF squid. If an oscillating current I is passed through the LC circuit from the RF source, now a magnetic flux RF will be induced. Thus the total external flux will be flux external is equals to flux plus flux RF. If the flux phi is in the loop changes, there will be corresponding changes in flux external, as the loop is linked to the LC circuit through mutual inductance. The change in total flux external will induce EMF in the LC circuit following Faraday's law. Thus, there is a change in voltage across LC circuit. By measuring the change in voltage across LC circuit, one can measure the external magnetic flux and its variation with respect to time.
Thank you for watching. Do like, share and subscribe to my channel.